Hello. We'll talk today about determinants. That's quite a tricky thing, and I will try to have things simple and to learn a lot of things about the determinant. Basically, everything that you need to know in the real case. So let's find this presentation. Here we go. So the determinant of real matrices. It's going to be real matrices because we started with real matrices, but later we'll do a complex case. It's exactly the same. So, what's the definition of the determinants? This is quite tricky, and even professionals like us, calculus teachers, don't all agree because you have all these properties of the determinant, and there are 3 or 4 statements, and each of them can serve as a definition. So it depends on the taste and everything. So I'll explain you here the old style definition. That's how people found the determinant. I mean, long ago in time, and that's still the best definition in my opinion. I mean, you can do better than this. So the idea is that the determinant is basically of a system of vectors. It's basically the volume of the parallelepiped formed by these vectors. Okay, so in 2 dimensions, for instance, you have these vectors. You can make a parallelogram, you compute that area. In 3 dimensions, you make a parallelepiped, you compute that volume, and so on. So that's the determinant. I mean, it's very simple and extremely useful. For instance, if you want to check if the vectors are linearly dependent or not, linearly dependent means that the parallelogram there will degenerate somehow. So the volume is 0, the determinant is 0. So that's the good definition. Now, there's a problem. This is not exactly the determinant because this is the absolute value of the determinant. So we'll see that in a second. So let's put this sign here. That plus of a system of vectors v1, vn is the volume of the parallelepiped. Okay, so it's a positive number. So let's see what we get. This is definitely very interesting for applications and everything, computing these volumes. Now let's try to find a formula for this function, that plus. And for that, well, we go in 2 dimensions. So here's your formula. If you take 2 vectors, AC and BD, what you get if you compute is AD minus BC. So how to prove this? It's a plane geometry thing. So you have these 2 vectors here, make the parallelogram. You have to show that the area of the parallelogram is AD minus BC, but AD is the area of a rectangle. You put A here, D here. The same for BC, right? You put BC here, C here, C here. So finally, we have to show that the area of a parallelogram is something like this, a difference of 2 rectangles. You can, yeah, I'll leave this as an exercise. You can solve it in puzzle style. I mean, cut the parallelogram somehow like this and rearrange things as a puzzle, and you get the difference of the 2 rectangles. So this is very nice. Of course, we have to put absolute value here because it's a positive number. So this is very nice, but it would be actually even nicer if somehow we modify the definition of this that plus as to get AD minus BC, not the absolute value. Why? Because AD minus BC is a very nice quantity. It's linear in A, B, C, and D, right? It's linear in A, B, C, D. So that's going to be much, much easier to compute than this absolute value. So how to do this? We have to introduce a sign somehow. I mean, the determinant as defined before, it's not exactly the volume. We have to put a sign here for things to be easier to compute. And here's your definition. So it's indeed the sign volume of the parallelepipeds made by these vectors. And the sign comes in this way. So a system of vectors v1, vn is oriented if you can pass to it somehow continuously to the standard basis of Rn. Okay, so here's my standard basis of Rn. Here is v1, vn. If I can do this, pass continuously to the standard basis, the sign is plus. It's called oriented. If not, if it's somehow upside down and you cannot do it, the sign is minus. So with this, if we go back now into dimensions and see, well, here we didn't really prove it. I mean, I just told you that's the idea, and I left you as an exercise to do the proof. But if you do the proof and check now when this is positive, this is negative, it's precisely positive when the vectors are oriented. I mean, they're like this, first one, second one. and it's negative when it's the other way around. That's the first vector, that's the second one, but it's not like the standard basis. So this means that the formula is exactly the one before. Let's go back to it, but we have to remove the absolute value. So this is nice. This is very nice because it's linear at some point A, B, C, D. So that's the good definition of the determinant. It's the sign volume, the parallelepiped made by the vectors. Okay, now let's try to compute this from properties. So first of all, for a matrix, that's for a system of vectors. Now this system of vectors, you can say that it's the columns of a matrix. So we'll write that A for that matrix for just A between bars. That's the convention. Now also matrices, remember from last time, these are the same as linear maps from Rn to Rn. So given a linear map written like this, you can call about its determinants, but it's not. It's actually inflation coefficients of f. It's better to say this way. So inflation, because if you think a bit, what are these vectors of the matrix? These are exactly the images by f of the standard basis of Rn. So here I have the standard basis of Rn that you can complete into a cube like this, and here you have the image by f that you can complete into a parallelepiped. So the volume here is finally the inflation volume-wise somehow done by f. Okay, so that's it. That's the determinant. It's defined for a system of vectors. Okay, now for a matrix, it's the same thing as a system of n vectors. You can talk about determinant of a matrix. And linear maps, it's one more thing, which is the same thing as matrices or systems of vectors. And here it's better to think it as an inflation coefficient. Now theorem, let's work out some properties. So first of all, it's a linear function of the columns. And then we have that AB is that A that B. And as a consequence, if this is true, of course, that of AB is that of BA. So if this is true, well, the linearity, you have to do a bit of geometry. I mean, you see, I need to prove this, that if I add two columns, it's additive. And also, if I multiply a column by lambda, I get the lambda here. So that's, you can do some geometry. It's not very complicated. You get these things. Now the second formula, which is, well, this is really scary. I mean, if you use other definitions for the determinant, it's very hard to prove this, okay? But for us, it's trivial because best is to think of it in terms of linear maps. So you see, we have FAB is FAB. That's something that we discussed about last time. Now, if you look at the standard, the cube there, okay, gets inflated by FB and then by FA, each time by the determinant, okay? So the inflation coefficients of FAB is this product that A, that B. But FAB itself, you can say that it inflates, but that AB, right? So that AB is that A, that B. It's trivial, this definition. As a consequence, of course, you get that AB is that BA from this, right? This is also scary. I mean, if you use other definitions on determinants, it's complicated. So very nice. I mean, just by doing a bit of geometry, you have to do it here. We have all the good properties of the determinant, including this scary property that AB is that A that B. So everything is trivial, this definition. Now, what else can we say? Assuming that the matrix is diagonalizable with eigenvalues lambda and lambda n, the determinant is just the product of eigenvalues. Why? Well, I mean, it's clear from the inflation viewpoint. I mean, the associated linear map, if you, in the basis of eigenvectors, multiplies by lambda 1 here, lambda 2 here, and so on. So in the parallelepiped, if you compute the volume, it's, of course, it's lambda 1 times lambda n, right? Alternatively, well, you can get it with matrix calculus. I mean, let's get it from this, that AB is that A that B. So diagonalization means this, A is PDP minus 1. So now, because that AB is that BA, I can put this P here, switch it to the right, so I get just the D. But the D, I mean, when D is diagonal, you can get it by linearity. I mean, by linearity, you can take a lambda 1, put it in front of your computation, and then a lambda 2, and so on. So you get this, times the determinant of what's left identity, which is 1, of course. So that's it. But again, I mean, this is just an illustration for this matrix calculus. I mean, inflation viewpoints trivialize everything. Now, what else do we have? Well, this is something useful which follows from what we did. So I take a matrix once again. So first column vector, second one, and then some other guys. And I can always subtract from the first column the second column multiplied by lambda, same determinant. Why is this true? Well, I mean by linearity. I mean this is that u and the other guys, what we want to get. And then we have that lambda VV and the other guys. But lambda by linearity goes in front. And that VV other guys, well, it's zero because the paralleliped degenerates. I mean, it's not a true paralleliped. Two vectors coincide, so it's splashed there. The determinant is zero. Now, once you have this, well, you can use this kind of tree for an upper triangular matrix now. So remember, for a diagonal matrix is the product of eigenvalues. That's a generalization of this. For an upper triangular matrix is the product of the diagonal. And same, of course, for the lower diagonal ones. So this follows from this. I mean, this thing here, you can reduce this matrix to a diagonal one. Now let's see some explicit examples. Now we have a lot of theories. So in 2 dimensions, of course, it's AD minus BC. That's something that we know by geometry, by that puzzle method. But now we can also, as an illustration for this theory, we can recover it because was the simplest thing to be used. Well, this thing here is quite powerful. So let's subtract from AC a suitable multiple of BD. So the factor lambda should be C over D. Because if you put this factor, you get a zero here. Now it's upper triangular, so it's a product here. So you get AD minus BC. Very good. Now the same formula can be used in 3 dimensions, but I mean the same method somehow in Gauss method, putting it in upper triangular form. But we'll not get into it because I'll show you in a minute a more conceptual proof of this. So you get this formula here, which is called the Sarus formula. And this is very useful. So in order to memorize this, you see you have 6 terms, A, EI common plus, and then you have 2 triangles, BFG and CDH, which are somehow parallel to this diagonal. Then you have 3 negative terms, which are this, CG, and 2 triangles which are parallel to the other diagonal. So this is a way of try to memorize this. This is extremely useful. For the proof we'll see in a second. I mean, definitely it can be proved that like in 2 dimensions with Gauss, but we'll see in a second more conceptual proof. Other examples, what do we know? Transformations, projections, symmetries, rotations. So for a projection, you get 0 unless the projection is the identity determinant is 1. Why? By inflation, in the projection splashes is there, so it's 0. This is the identity. Of course, you can get it also diagonalization. So the projection is diagonalizable. You have ones on the image and 0 outside. So if you make the product, basically get 0, unless you have only ones, and you get 1. Now, projection symmetry is now for this matrix here. The symmetry. You can get it in all kinds of ways. I mean, either with inflation or eigenvalues, or we get -1. Rotation of angle T, once again, basically by inflation. I mean, if I take the square there, how is the square inflated by rotation? Well, the rotated square has the same area, so it's 1 as the determinant, but you can get it also with the formula of the rotation and trigonometry. But you see, I mean, the inflation viewpoint is very good because you don't need the formula of this and trigonometry. It's just trivial. I mean, the square you rotate it has the same area, determinant 1 over. Okay, so as a remark, what we got so far as determinants, you see 0 or 1 here, -1, 1. So the usual basic matrices tend to have determinant 0 or 1, -1. So we'll be back to this. This is part of a general phenomenon. It's about rotations, orthogonal matrices, things like that. So we'll be back to it. Now let's develop some more theories. So first of all, something that we've seen already, the determinant can be fully computed by using this Gauss method, namely by linearity somehow, subtracting the Gauss and multiplying it by scalars. That's something that we know. And as a consequence, the determinant viewed now as an abstract function. You see, I mean, it takes as input and vectors, and the output is a real number. Of course, it's linear, it's alternate. I mean, due to the fact that it's a sign volume, whenever it switches to vectors, the sign will switch to. That's what alternate means. And unital means that if you take standard basics, you get 1. It's unique with these properties. Why? Because of this. I mean, such a function also can be compared to the Gauss method, right? And it's unique, so it can only be the determinant. So this is something useful. I mean, it's, some people even take it as a definition for the determinant. It's a bit crazy, but it's quite useful. We'll use it later. Now, let me give you a formula. So we've seen, let's go back to the slide. So you see you have AD minus BC and then this sorrow thing. So what's that for now? The formula and so on. Let's do something with permutations. You see, so you somehow, when you pick up your entries there, you kind of permute. So let's talk about permutations now. I'll give you the formula. So permutation of one n is just a bijection. There are n factorial of them because well, if you want to construct such a beast, you have a choice from sigma of 1 and choices, then sigma of 2 and minus 2 choices and so on. So you get this factorial. Now, let's define a signature of a permutation to be number of inversions. By inversion, I mean you take I smaller than j, and then you get the sigma of these guys. If sigma of I remains smaller than sigma of j, nothing happens somehow. But it can also get inverted, right? So the number of inversions is the signature, minus 1 to the number of inversions, as the typo here. So if the number of inversions is odd, the signature is minus. The number of inversions is even, the signature is plus. So now here's the formula. The determinant is just a sum of entries of the matrix. So pick one from each row, but the index of the column must be a permutation. Okay, you don't have to, you cannot pick like this and this right below. You have to move all the time. And when you move, you have a permutation and you put the signature of that permutation here. So proof here by the Gauss formula or the abstract characterization of the determinants. I mean, this beast here also is multilinear, whatever, so you can get it like this, okay? And as an illustration, let's go back to Saros. So you see, I have to pick things. I have to pick one from each row and then permute the index of the column. So A, for instance, if I pick A, I can only put either EI or FH, right? That's this term here and the last term here. And now the sign, if I pick AI, I mean, there's no inversion, that's the identity permutation times plus. But if I pick F and H, we get a minus because it's an odd permutation. So I have to work a bit. I mean, there are 6 terms exactly, it's permutations. Okay, so that's the formula. Now, in general, if you take a 4x4 matrix, for instance, you have a kind of Saros formula there. So how many? 1 times 2, 3, 4, there are 24 terms. Okay, so you can write a formula of 24 terms if you want. So, and so on. I mean, 5, 5, it's 5 factorial, 120 terms. So it can get very, very complicated. Finally, as the last thing, I mean, this is really useful for, we said last time that the important thing is to diagonalize matrices. And here's your theorem. The eigenvalues must be roots of the characteristic polynomial, which is that of A minus lambda. So why is this true? So that's why the determinant is very important in connection on eigenvalues. So given a vector, A v is lambda v, that's the eigenvalue condition, is equivalent to A minus lambda times v is 0. Now this has no zero solution when this matrix is not invertible. So this matrix must have determinant 0. That's the characteristic polynomial, which must be 0. Okay, so very important. All these determinant things, they're useful for many things. Basically, it's to see when a matrix is invertible or not. That's very good. And that's an excellent application of it. The eigenvalues must be roots of the characteristic polynomial. So I'll be back to this in the next lecture when I'll get into diagonalization next time. See you soon.